So what happens if in this optimal depletion we introduce inequality? So the depletion is optimal, but the kappa is 100. So the rich earn 100 times more than the poor. And so if this was what I showed before, and with the scale changed because it increases up to 500 years, they are exactly the same. And the elites are in red, and they very slowly start growing. And what happens after that? What we plot here is the population of the elites multiplied by kappa, because the equivalent is 100. They use 100 times more, so the equivalent consumption is this. And what happens is that once the system reaches that equilibrium, and the appearance of the exponential growth appears in the elite, the consumption of wealth starts decreasing the wealth, and as soon as the wealth decreases, the commoners start dying because of hunger, so to speak, but the elites are perfectly happy because they are still growing like crazy for a couple of centuries, so they don't think that they need to worry, but they also collapse after this. So this is a type of collapse which is due to scarcity of labor. We assume that the elites don't work and the commoners are not there to do. So what happens if we have both a high inequality, like in this case, and high depletion rate? Then we have a much smaller carrying capacity, and nature takes a couple of 100 years to get strongly depleted. The wealth at the same time grows until the growth is excessive, and the commoners, as the wealth goes down, the commoners start reducing the population because of famine, and the elites last much longer. And so it's an interesting thing. Is there any hope in this model for an unequal society to survive? And inequality is very, very important, but and the answer is yes. We can survive if we reduce the depletion per capita, the inequality, and slow down the population growth. It is possible to reach a steady state and survive very well. So reaching this equilibrium requires changes in policy. So reduce depletion per capita, reduce inequality. For example, we did this run with kappa equal to 10, so the rich make 10 times, not 100 times more than the poor. And this is what Daly estimated, and also reduce birth rates. And in the situation that we are now, we are consuming more every year than nature produces, because we are using non-renewable energy. So what happens if we add to this model, which had only natural regenerative nature? So for nature is, for example, woods that are crops and fish that are regenerated every year until we overuse them, and then they collapse. So this was the collapse that I showed you before, and so we assume that in addition to the regenerative nature, we have we add fossil fuels, a large amount. So this is what happened. This collapsed at about 500 years. So and the maximum population, which is just the maximum population for this model was 80,000. And now when we added the non-renewable resources, the collapse happened 200 years later. So the non-renewable resources pushed the collapse to 200 years later. But the peak population increases by a factor of 20. And this is incredibly similar to what has happened with the Industrial Revolution. We put this non-renewable, we got access to a non-renewable large source of energy, and that has allowed us to push about 200 or more years, but the population has increased by a large number, similar to 20. So this is what happened. What's been happening at this point. So since 1950, we double our total consumption of Earth resources every 20 years, and so this is a very worrisome situation. So non-renewables. What the use of fossil fuels or non-renewables did was to expand the carrying capacity together with the technology. So we could use more population could be supported, at least, but not forever. So fossil fuels are stocks of energy and material resources accumulated of several hundred millions, and we are consuming those stocks in 3 centuries. And it's also worrisome that a similar dynamic takes place with aquifer water. In just a few decades, we are drawing down vast stores of fresh water from aquifers that take centuries or millennia to recharge. So again, by adding fossil fuels, we postpone the collapse by 200 years and increase the population. So this is the last another model that we developed, that it's called coupled water model, COWA. And we developed it for the Phoenix watershed because it has very good data observation. So we validated it for all the observations that are available from 1900 to 2015. And the idea is very simple. If there is enough water per capita, population continues growing by immigration and births. If water is not enough, population migrates out or has a greater death rate. So if there is enough water, the population increases because Phoenix is a wonderful place to be. But if you run out of water or not have enough per capita, the people leave or have a greater death rate. And this reproduces quite well the observations. But if we estimate the future, these estimations are for the future in full lines are made by the census bureau, which, like the United Nations and IPCC and the integrated assessment models, do not couple with feedbacks the human system. So they just extrapolate the exponential or whatever the growth is, use demographic rules to extrapolate. And so the population, for example, would go to 45 million in 2100, which is ridiculous. Whereas our model, we knows that the systems are coupled and you cannot have 45 million, so it has 10 million. So we need to replace fossil fuels with renewables. So this is a summary of what I have, and then I have an appendix which is this thing, and I don't know if I run out of.
You still have time.
What?
10 minutes. You have
10 minutes. Well, I went too far. So this is the summary and we are using in 200 years what nature accumulated over hundreds of millions of years, and same with fossil water. And the use of fossil fuels in agriculture increased food production after 1950. And Handy 1, which we think is a model for thought experiments, shows that reducing social inequality, population growth, and depletion per capita allows society to become sustainable. And adding non-renewables increased the population by 20 times. And if the transition from fossil to renewables, solar and wind, is done early enough, it is possible to avoid the collapse. But it's very important to know that even IPCC and even the integrated assessment models, the best we have now, are not modeling the coupling Earth's human system. So we need to couple to provide feedbacks. And otherwise, for example, the Phoenix population would be expected to reach 45 million. So let me talk about the appendix. Can we replace fossil fuels with renewable energies? Is that possible? And could we put them in the Sahara? And if we do that, we will have to have very large farms of wind farms and solar panel farms, and that will have a climate impact of very large. So we should explore what the climate impact of very large solar and wind farms is, and because otherwise it's like an unintended geoengineering experiment. We need to know what will happen. So we did